All right, so I'm here at Lambda World to talk about what happens when you've won the revolution of functional programming, because I'm declaring victory. We have won the war of ideas. When I started in graduate school 20 years ago, I had to explain to programmers that there was a thing called Lambda and that there's this idea called functional programming. And now Java has Lambda, C++ has Lambda, Python has Lambda, everyone has Lambda. Now 17 million Java programmers are figuring out what Lambda is, but it's happening, right? I mean, it only took since when? The 1930s with John McCarthy until now, but slow progress. So even though not every programmer is using functional programming, the ideas of functional programming, ideas like immutability and the idea of anonymous functions and those sorts of things, I think those ideas have become accepted. Certainly, they've become accepted at the level of programming language designers. Okay, so you can see that new languages incorporate these ideas, and older languages are being retrofitted to have functional programming ideas. So what now? Okay, so functional programming 1, everyone's got Lambda, great. So what? What happens now? Is it just more Lambda? You know, if Lambda doesn't solve your problem, just use more Lambda. Is it that sort of thing? Or is there something else to think about? Now, one approach obviously is, much fancier styles of functional programming, and there are people who are exploring dependent types in various ways, or homotopy type theory, and trying to figure out how category theory can be applied. All those sorts of things, and those are fine things to look into. And we have gradual typing and all those. So lots of exciting work going on. But I would also claim that there are other paradigms of programming that have some advantages over functional programming that it's worth revisiting. Okay, so functional programming has been around for a long time. The ideas of functional programming have been around for a long time, and it took a while, for everything else to catch up. And you could see in the early days of Haskell, they had little problems like they didn't know how to handle input and output, which if you try to explain that to, a COBOL programmer in the 60s, well, we got this great language, but we don't really know how to do input and output with it. That wouldn't have flown. So they figured out the input and output. And, so there's functional programming, but functional programming is not as abstract as it could be, and it doesn't have all the properties that you might like. Even languages like Haskell, I would claim, aren't as abstract as you might hope for. In that there are other paradigms worth exploring that have been around a very long time, and for whatever reason haven't really seen the renaissance that functional programming has. And in particular, I'm talking about logic programming. I think logic programming has a problem, and the problem was that early on, this language called Prolog sort of ended up dominating the logic programming space to the extent where, today, if you look at different logic programming styles like data log or answer set programming, you will see that they generally use like Prolog syntax, and you can think about them in terms of sort of different variants of Prolog and different expressiveness. You even have things like Erlang, which has syntax from Prolog, right? And so if you go to a logic programming conference, you will find that Prolog to this day is in the air to an extent that it's almost hard to believe. So in functional programming, it'd be like if all functional programming today had to be done in Lisp 1.5. Okay? So yeah, we could figure it out. We could do it, but you're never going to have Haskell. You're never going to have OCaml if everything has to be done in Lisp 1.5. There's just certain things that are hard to escape, certain design decisions that were made that are so difficult to undo. And I think that's the state of logic programming right now. And in particular, Prolog, the main logic programming language, was designed in the early 70s, say 1972-ish, something like that. and was designed to solve problems on hardware of that time. Very, very modest, very small amounts of memory. And Prolog made a bunch of design decisions to take that into account. For example, by default, Prolog uses a search, a depth-first search, which is called an incomplete search, where you aren't guaranteed to find all answers when you search across a problem space. That was designed for efficiency. And if you're on a computer with 64K of RAM, that's really critical. But my laptop has 64 gigs of RAM. And so we're living in a somewhat different time. So why should I be constrained to a language designed to run on a computer with 64K of RAM? So that's a question I ask. And also, just like early days of Lisp and even languages like ML, they involve side effects and mutation all over the place. And, it took a while to figure out how to do things in a more pure style, like in Haskell. So that's the sort of situation I see logic programming in. It's been around for a long time. It's been around since the early 70s. There was a major effort to try to use logic programming in Japan in the 1980s, the fifth generation computing project, which either succeeded or failed depending on who you talk to, but I think the outputs of that project didn't really end up in the languages we use today, for the most part. You could sort of look at the parallels, because in the 80s there was a lot of interest in Lisp and Lisp machines for expert systems, and also in Prolog for expert systems. So there was sort of these two paths, and the two main languages for symbolic AI were Prolog and Lisp. And, the Lisp stuff, other languages coming out of sort of the tradition you can get with Lisp, we got functional programming out of it, and that's been very successful. The logic programming stuff, I would claim, hasn't been successful, not to the same extent. We have restrictions of logic programming, like data log, which is sort of like SQL and then some. It's somewhere between, SQL and Prolog, you could think of it that way. And we have this thing called answer set programming, which is very interesting, which is, also can be seen as a subset of Prolog syntax. You usually have syntactic restrictions. But full Prolog, sort of, it's in kind of a backwater situation. And I think that's partly because Prolog made a bunch of decisions and embraced a model of computation based on logical side effects, I'll call them. Okay, it's very impure language, in the same way that old school Lisp is very impure. Is not exactly Clojure. Okay, so we don't have the equivalent of Clojure for logic programming, but we do have this family of languages called miniKanren I've been working on with many other people for the last 20 years. And I want to show you a little bit about what we can do with miniKanren. And I've given many talks on miniKanren, but in particular at this point, what I want to draw your attention to is that there are other paradigms besides functional programming that I think are worth revisiting. And I think logic programming is one of them, especially very pure constraint logic programming. And also, you can combine functional programming and logic programming in interesting ways. And that's also an area where there's been some action recently. So there are older functional logic languages. Curry's a famous one. Mercury's another. But there's also a new language called Verse from Epic Games that has a bunch of very famous functional programming language designers working on that. And so that is a mixture of ideas from functional programming and logic programming. I think it feels more to me like that's more logic programming, and also it feels like, more functional programming, and also feels like it has elements of some other styles of programming, but you can see in the air that people are revisiting it. So just from talking to people at Lambda World, every time I mentioned logic programming, the response I got was, well, I've heard about logic programming, but I don't know anything about it. So, sort of the big message is I would advocate that you learn about logic programming and think about it, and think about how you might use it. Okay, so I want to show you some miniKanren. And I also want to show you something that I wrote, last night. One of the problems with this miniKanren language I was going to show you is that it really is a domain-specific language for pure logic programming or constraint logic programming. And it didn't really have a functional story, even though usually we embed it in a functional language like Scheme or Racket, that type of thing. However, you can't mix the functional parts and the logic programming parts in a nice way. So it's never really been a functional logic language, even though you have a functional host language like Scheme and you have a logic language embedded. So last night I fixed that, or actually this morning I fixed it around 4 a.m. And I'm going to show you. Now, like I said, this is kind of like the early days of Haskell where we don't know how to do input and output, that kind of thing. It's like we're not quite that bad, but the performance story needs some work, okay? With the exception of probabilistic programming, this is probably the slowest paradigm I know of, but we do know ways to speed it up. For example, staged evaluation. I'm working with Nada Min and Michael Ballantyne, Jason Heeman to try to do staged versions of these evaluators. And also there's approaches like super compilation that people are investigating. All right, so let me just show you a little bit of miniKanren. It's a very small language, so there's not much to see. And first I'm going to just show you a real quick refresher of Scheme, which is a Lisp. And since this is Lambda World, I don't think this is going to be too surprising, but let's just make sure everyone's on the same page. So, Lisp usually has some notion of lists. So I can say list 3, 4, 5, and I get back a list. Okay, that's a list. I can also cons up a list, and I have quoted symbols. I can cons symbol cat onto cons of symbol dog onto, quote, the empty list. That also builds up a list. Okay, so we have lists. We have the ability to create lists. We have the ability to get parts of lists. So I can get the first part of a list using an operator called char. I can get the rest of the list with an operator called cdr. We've already seen quote. I can also quote lists. So I can say, rat and bat. Okay, so we have quoted lists. And we also have something called quasi-quotation or a back quote, which is used for almost constant data. So we also have things like let. So I can say let X be the car of the list cat bat. And then I can say that I want to create a quasi-quoted list. I want the value of the let expression to be a quasi-quoted list that has dog, comma X, comma mouse. Mouse, no comma there. And what happens is the comma X, that comma cancels out the quasi-quote, so it's as if I had just written the variable X there. Okay, so that's a handy notation that we'll see a little bit of. This is equivalent, by the way, to doing list of quote dog X, quote mouse. Okay, same meaning for those two. And then, of course, we have our friend lambda. So I can say lambda xy plus xy, and then I can do an immediate application of that to, say, times 3, 4, and 7. Okay, it's our standard thing. I can give a name to something with define. I can say define x to be 5 and refer to it. And I can also do things like letrec for defining recursive functions. And so I might define append, and append might look like this. So I can say I have 2 arguments which are lists, and I'm going to say if the first list is empty, that's null, then I will return the second list. Otherwise, I will cons on the first thing in the first list to the recursive call of the rest of the first list to S, and then in the body of the letrec, I can call append. So I can say append ABC to DE. That works the way you think. And then the last thing I should show you is eval. So you've probably seen languages that have eval, so we can evaluate data as if it were a program. So I can quote something like +3,4. Let me just show you what that looks like. So if I have something like +3,4, okay, that's an expression that's evaluated, but I can quote the expression, and now it's treated as data, so now I get a list back, and I can do things like take the car of the list. Okay, no problem. And then if I want to, I can call eval on the list, and I can evaluate that quoted list as if I just written the expression. Okay, so eval and quote sort of are like opposites. Okay, so that's all of the scheme that we need to know. Notice that for append and for eval, these are functions. Now, maybe that's not surprising because this is the world of functional programming, right, that we're in, which we're about to leave. So the idea of functions is bad. We shouldn't be using them. The idea of inputs to functions and outputs of functions is bad. That idea shouldn't exist. We should talk about relations. We shouldn't say that append has two arguments that are inputs and returns a list as an argument. Okay? The notion of inputs and outputs, bad. That's in the relational world. Okay? In the functional world, sure, inputs and outputs are great. In the relational world, we're going to get away with, or do away with them. And so in the relational world, eval will take an extra argument. That extra argument is the value of the expression that's evaluated. In the relational world, append will take an extra argument. That extra argument is the value of the first two arguments appended together. Okay, so in the relational world, we're going to change up things, and we're not going to have notions of input and output anymore. All right, so let's just show you some miniKanren now. I'll show you one more thing in Scheme that's useful to know. So I can do something like this. All right, so I can write down equal question mark, which is a predicate which compares the values of two arguments, and will give me a true value, which in this case hash t. Anything other than hash f in Scheme is true. So we have hash t for equal. Otherwise, we'll get hash f if they're not the same value. Okay. So, and this is recursive. It operates recursively over whatever structure we give it. Okay. Now, the main operation in logic programming is what's called unification. And it's a constraint. And you can think of it as sort of a generalization of something like equal, or a generalization of pattern matching. You can think of it as a two-sided pattern match, where you're allowed to have variables representing unknown information. So I've already loaded miniKanren, so we're in Shea Scheme, but I've loaded the miniKanren extensions, and the equivalent of equal in miniKanren is this equal operator. So I can do list 3,4 and list 3,4. Okay, I am writing a constraint asserting that those are the same, that those would be equal question mark if you want to think of it that way. Now, if I try running this, I get back a procedure. And the reason is Scheme doesn't know anything about logic programming. Scheme only knows about Scheme. So even though we've extended Scheme with certain operators like equal, we also have to make sure that we have the ability to interface between our host language and our object language. And the way we do that is with an operator called run. Okay, so this is inspired by monads, that type of thing. So if we want to get an answer in our Scheme land, we will write something like this. So we'll say run one q. Q is just convention for what we call a query variable. And then we can have what's called a goal, or technically a goal expression, as the body of the run. So here I'm saying I want one answer, if it exists, and my query variable q is sort of the object of interest, and I have got some constraints. So I'm saying, I'm basically asking for which value of q is it true that the list 3,4 is equal to list 3,4? Well, for every value of q is the answer, And so we get back this placeholder value, which is _.0. That represents, well, could be anything. Whenever you see an underscore dot something, that means could be anything. It's more interesting if we put the query variable inside one of the lists. So now we're saying, for which value of Q is the list Q4 the same as the list 3-4? Well, in that case, when Q is 3. Okay? And we can also, if we want to, put Q in both positions. And in this case, it's not satisfiable. We've said that Q simultaneously has to be 3 and 4, so that's not possible. So we get back the empty list of results. Okay. We also, in addition to being able to ask questions about or assert things about equality, we can also say that we want more than one choice. So that's something called kandi. So I can say here that either Q is 5 or Q is 6. Okay. These choices, these clauses, this looks like a con clause, McCarthy's con in Lisp. These two choices or clauses each have one goal, which is a single unification, or called equal. And so I'm saying there's a world in which Q is 5, and there's a world in which Q is 6. And those are separate worlds. They don't interact with each other at all. They don't know about each other. There's like a many worlds interpretation of logic programming, if you want to think of it that way. And I've asked for one answer, so I only get back one answer, 5 in a list. I can ask for a second answer, and I get back 6 as a second answer. I can ask for a third answer, and there are only 2 answers, so nothing more to be said. Or I can ask for every answer with run star, and I get back the list 5, 6. Okay, so you've already seen 2/3 of the language. So I'll show you the last operation in the language, which is fresh. Fresh allows me to introduce new logic variables like the query variable. But if I want to see the value associated with these locally introduced variables, I have to make sure that the query variable is involved somehow. So I can do something like say, oh, I want a conjunction. There's an implicit conjunction here of X and Y. I want the list X and Y to be associated with Q. And I'm going to say in one world X is 5, and here's another conjunction within one line, one clause, and Y is 6. And in another world, X is 7. Okay. And now if I run this, I'll see that I have 2 answers. There's a world in which X is 5 and Y is 6. Remember, we're seeing the query variable Q, which is associated with the list of X and Y. And then there's another world in which X is 7 and Y can be anything. I could even do something like, say, make X and Y be the same. And now we see that X and Y can be anything, but they have to be the same thing because they have the same number associated with them. Or I could say, let me say, I will, in the second clause, 8 is 8. Well, that's always true for any value. So you can see that that's true for any X and any Y. And because the numbers are different, that means those could be different X's and Y's. Okay. So that is the core part of the language. We have a few extra constraints that we use for writing interpreters and things like that. The main other thing to know about is there's another constraint called a disequality constraint, where we could write things like Q is not, 9. So that means that Q can be any value whatsoever except for 9. In this case, it doesn't really matter. But that's enough of the language. We don't need to know anything else. There are a couple more operators to help us write things like interpreters. Now, when you have a language like this is kind of like learning Lisp for the first time. It's like, okay, great. I've got lists. Well, how do I write a program with lists? It's the same thing here. Like, that seems pretty Spartan. How do you write programs with this little language? Now, we inherit a little from the host language, so we have things like define and the ability to write recursive relations. So let's just do kind of the hello world very quickly. So we'll have define appendo. This is sort of the standard thing that you would see in, say, prologue, and we'll say condy if L is the empty list, then S is L plus S. Otherwise, we're going to have to introduce some temporaries, and then we're going to have a conjunction of goals inside the fresh, and that's going to be if the first list happens to be cons of A onto D, it's a pair, and then in that case the result will be consing A onto res, and then we have this recursive call to appendo on D S to get res. Okay, now that may not make a lot of sense to you, but at least you can see that I only use those operations I showed you already. Now, I can play the game with appendo that we like to play with logic programming. So I could say we got ABC, and I have DE, and now I have a third argument because appendo is a relation. I could say if I append ABC to DE, what is, the concatenation of those, and I get ABCDE. Now, that wouldn't be very exciting, except, of course, that what we can do is we can take the third argument, and now we can place our query variable some other position. So now we can solve backwards. So it's like an algebra problem where we have variables representing unknowns, and underneath the hood, miniKanren's using a combination of search and constraint solving, like unification as a constraint, to try to figure out what is a value of Q that will satisfy this. We can also do multiple query variables. So I could say X and Y. So I can say X and Y. And so now I get a pair of values that when concatenated together gives you ABCDE. And I can even ask for all the answers. And now there are 6 pairs of answers for X and Y. There are lots of more, I could put logic variables inside of lists and things like that, okay? And I can have as many logic variables as I want. I can have logic variables appear multiple times. I could have X appear multiple times in different positions. So there's a lot of flexibility here. So this is the sort of thing you see in a prologue book. If you read a prologue book, they'll always have this example. And then maybe the first 3 or 4 chapters will say, yes, you can do this, and you can write programs this way, and I'll show you how. And then the rest of the prologue book will be saying, but you can't really do it, so we'll show you how to write the nasty version. All right. So it's sort of like a Lisp programming manual from the 60s or something saying, yeah, you can write things as functions, but that doesn't really work. So here's how to do mutation and side effects. So the idea of miniKanren is, well, what happens if we take this seriously and we want to write all of our programs this way? We want to write everything as a relation, which is really the promise of relational programming or pure constraint logic programming. We want everything to work this way. So what's another program that we could write besides append? Append's not all that exciting. Well, one thing we could write would be an interpreter for a programming language. How about an interpreter for scheme or a subset of scheme? So we could do that. Let me load a little interpreter for a subset of scheme. Okay, so we've already seen that we have eval. So we know that we can do things like eval quote cons 3, 4. Okay, so we can eval a quoted expression. Now we have evalo. By convention, we name our relations with an O. I guess it sounds kind of Spanish. So we have evalo instead of eval. And evalo, because it's a relation, is going to take 2 arguments. So it will take an expression and a value. Okay. Remember, there's no notion of input and output anymore. It's just 2 arguments. Now, of course, we need a run interface. So we could say run1 q, and we can call evalo. And I could say, well, how about quote of cons of quote cat to the empty list. And I'll say that the value of that cons expression, we'll call that q. And do I not have cot? Maybe I have lists. Yeah, okay. I have a baby interpreter loaded that doesn't have cons. It's too complicated. I just have list. Okay, so we can see that if I evaluate list of quote cat, quote empty list in my relational evaluator, I get cat empty list. So I guess I'm going to make it cat dog. Okay, so now we have a list of cat and dog. But of course, the interesting thing is that we can put our logic variable in the expression position. So I can say, I love Lambda World, okay, and say, give me an expression in my little subset of scheme that evaluates the list I love Lambda World. Quote, I love Lambda World, that's one. Okay, how about 99? Okay, so here we have 99 of these. So here's an example where we have a call to list, we have some quoted things, and then we have a few calls to anonymous functions with sort of arbitrary names for the variables. And if I evaluate that, and there's a call to list with no arguments, if I evaluate that, sure enough, I get I love Lambda World. Okay, and of course, it wouldn't be proper for me to pass up the opportunity to do a fun little example, which is there are these programs called quines, which are programs that either print themselves out or evaluate to themselves. Okay, and so you have some expression E, and the expression E should evaluate to E. Well, there we go. That's literally the simplest query we can write in terms of this number of distinct symbols. And okay, what do we get? We get this thing, okay, and some side constraints. So forget about the side constraints. That just have to do with the names. Okay, and I will replace the abstract names with concrete names to make it a little easier to read, and I run it, and sure enough, that's a quine. Okay, so this interpreter, which I'll show you quickly. Okay, so this is an interpreter that's written using our friends condy and fresh and equal and stuff like that. A couple other constraints, like there's something called absento in Symbolo, but those aren't very interesting. So the idea is that we can write an interpreter as a relation, and we didn't intend to have program synthesis when we wrote the interpreter or to be able to generate quines or whatever, but we get that behavior for free because everything's a relation and because we have search and constraint solving. Okay, and now the next thing you can do with this is, let me load a slightly bigger interpreter. Now we can go ahead with a bigger interpreter, do something like call evalo on a more interesting program. So in this case, this version has letrec, so we can go back to our append. Actually, let's see, do I have append? I do have append. Let me just grab this letrec append. Okay, so I'm just going to quasi-quote the letrec definition. Okay. All right, so this is just scheme code, okay? There's no relational code there. That's just, I ran it in Shea scheme, and you could see how it worked. Okay, so I'm going to run this, and I get back A, B, C, D, E, but because the interpreter is relational, I can just grab the A, B, C, D, E, and grab that list, put it in the, what you would think of the output position, the second argument to evalo, and now I can do things like put in our query variable x as an argument to the append. Okay, now you have to understand quasi-quote. So we have a quasi-quoted list. We have a quote for that argument, and then we have a comma. So that structure might look a little strange, but basically that just means we want Q to represent a quoted list. And so now we can take functional code and treat it as a relation because we wrote an interpreter for a functional language as a relation. Okay, that's the sort of thing we can do. And at that point you can start doing full program synthesis, and if we want to, we can start playing all the fun games. Like we could say, okay, well, we have X and Y, so let me just go ahead and get 6 answers back, and sure enough. So we can treat this exactly as we treated evaluate, okay? But by writing functional code, we can get the relational behavior. Now, what else can we play? Okay, so we can write relations, we can write functions because we're in Scheme, but we can write relations because we're in miniKanren. We can write an interpreter for a functional language as a relation, and write functional code, treat it as a relation. What else can we do? Well, how about we write an interpreter for miniKanren in miniKanren? Okay? Because miniKanren's a first-order language. If we look at things like the appendo, okay, I was able to put logic variables in the Scheme code. Actually, I'll show you one more example. I could put it anywhere in the Scheme code, actually, once I have that relational interpreter. But I can't put logic variables in this code because miniKanren has first-order unification. It's not powerful enough. So in the, just give you an example here. So I could say, if I have ABC to DE, I can go up there and replace that car of L with Q and say, all right, so give me a value of Q that completes that program, and it synthesizes that missing code, car of L. In fact, we can synthesize the entire recursive definition of append from examples. We got a tool called Barliman where we show that. Okay, so the cool thing is we could put logic variables anywhere, and that's one way you can think about expressiveness in this paradigm. Where can you put variables representing unknowns? It's like an algebra problem. Where are you allowed to put variables and have the system solve for it? Well, if we have a system where, or if we have an interpreter for miniKanren in miniKanren, then we can have examples like this. Okay, so let me load this quickly. Okay, so here is a simple example, but notice the structure. So we have a run star from our miniKanren embedded in Scheme, and then we have eval program O instead of evalo, and it takes a quasi-quoted program, which is a miniKanren program. So we have nested run stars. So we have, here's a condy, this is a simple example similar to what I showed you, and then the value of that run, whatever that inner run star, whatever that is, gets associated with a query variable X in this example. So I can try running it, and sure enough, I get cat dog as one of the answers. And I could start playing around with synthesizing miniKanren code. So now I have an example where I put the query variable inside the unification. Okay, so that's my query variable X, and I say that cond inside the run star should evaluate to the list cat dog. All right, and now miniKanren will figure out that actually cat would be a valid substitution there, and you can start getting more sophisticated examples. So, and then of course we can then start doing things like this. So now we have the ability to write evalo, which is the miniKanren relation, and run that inside of miniKanren. Okay, so now we had evalo at the top level. Now evalo is running in an interpreter written as a pure relation for miniKanren. So now we have miniKanren running on Shea Scheme. And so we can now start doing program synthesis tasks that way. That all existed. Bharath Joshi did this version of the miniKanren, which I've cleaned up and extended a bit. What I did last night was to go further. So I said, well, that's great that we have either a relational Scheme interpreter or we have a relational miniKanren interpreter. But the problem was, if you noticed, I was either in Scheme land or I was in miniKanren land. I couldn't mix those. So what I did last night was extend the scheme interpreter so that it's possible now to mix the scheme and miniKanren. And let me look at let's look at this one. Yeah. Okay. So here is an example. This is an example of a program where you can see that we're still calling eval programo. We have a letrec func. Now we have two types of letrecs, one for functions, one for relations, and we just have the scheme definition of append. But notice the body of that letrec are unifications. And so once again, we play this game where we can start putting in logic variables wherever we want and start doing synthesis. Start treating it like appendo. And then we can also start doing combinations of things where we take the scheme definition and the miniKanren definition, both running in the relational interpreter, and we combine them in a single program. So here we have a eval programo expression where we are combining the functional version of append with the relational version of appendo in the same program. And then we can run queries where I say, okay, when I run this whole thing, this combination of scheme code and miniKanren code, I want to get back the list cat, dog, fish, rat, but I have placeholders. I have 4 query variables, v, w, x, and y, and some of those are in the position of procedure calls, like I don't know what's being called. Some are in the definition of append and appendo. So I've put logic variables all over the place, and if I run this, it finds correct solutions for how I would fill in the logic variables in both the scheme code and the miniKanren code and in the calls to scheme and miniKanren. So this is a way to start combining functional and logic programming through writing interpreters for a functional logic language, and you can put logic variables anywhere you want and get the benefit of the search and constraint solving. So this is what I want to work on, staging and supercompilation and all the other tricks, and maybe with propagators and things like that, to see if we can make it more efficient. Okay, so that's what I wanted to show you, and I hope you all will be interested enough to learn more about this paradigm, because I think it's very interesting, and I think it will expand your way of thinking, not just about logic programming, but about functional programming as well. Thank you.